Hello everyone. This is the fourth lecture for the first day. Um, Today we started calculus and this is our fourth lecture. So day one, lecture 4. Alright, so we want to look at gradient of a function. Gradient of a function. In summary, to find the gradient of a function simply means to differentiate the function once. The first derivative of the function is what we refer to as gradient of that function. Okay, now I want to find the gradient of this function at this point, x equal to 1. Okay, so now we say y equal to x cubed minus 3x squared plus 5x minus 1. We want to find the gradient. So what do? We simply differentiate. We only need the first derivative. When you differentiate once, we call that one first derivative. When you differentiate it repeatedly for the second time, we say second derivative, meaning the result, or differential coefficient, or differential function. All right, so let's differentiate first. So we say dy upon dx. The power is 3, the coefficient is 1. So 3 times 1 is 3. We write the base. When we say 3 minus 1, it remains 2. The coefficient is minus 3. The power is 2. 2 times minus 3 minus 6. So when we say the power minus 1, we have 1. So whenever we differentiate 5x, it is 5. 10x is 10. Minus 8x is minus 8. So this is just 5. This one does not contain this x. So that makes it a constant. Differentiating a constant will give us 0. So we ignore it. Okay, even this one again, we can ignore the 1. So this is what? Our first derivative. The first derivative is what we refer to as the gradient. But the question for us is at this point, so what do we do now? We substitute what? 1 for x. Wherever we see x, we write 1. So we say 3 multiplied by x, which is 1, squared, minus 6, x is 1, plus 5. So 1 raised to any value is 1, times 3 is 3. 6 times 1 is 6, plus 5. So 3 plus 5 is 8, minus 6, we have 2. So this is the gradient of this function at x equal to 1. Okay, we have a more interesting one here. We want to find the gradient of this curve at the point where the curve crosses the y-axis. First of all, let's find the gradient. Y is x cubed minus 2x squared plus 5x minus 3. Here is the function that we are given. We want to find the gradient. Let's forget about the remaining part for now. Let's find the gradient and see what comes after. So to find the gradient is to find the first derivative. Finding the first derivative is differentiating once. So we say dy over dx. So 3 times 1 is 3. Then 3 minus 1 is 2. 2 times minus 2 is minus 4. Then 2 minus 1 is 1. We have another 5x. Differentiating 5x is 5. 5x is 5. Differentiating a constant is 0. Minus 3 does not contain this x, it is 0. So we forget about it. So we can simply ignore 1 again as a power. We already know that when we don't see anything at the power, it means there is 1. Okay, this is the first derivative, and this is what we call the gradient. Okay, so about this gradient, where do we need to find this gradient? at the point where the curve crosses the y-axis. Let us note these two. Um, One, at x-axis, y is 0. Then at y-axis, x is 0. Yeah. So at x-axis, y is 0. At y-axis, x is 0. So if we want to find the gradient at a point where the curve crosses the y-axis, at the y-axis, what is 0? X. So um, we say at x equal to 0. Why do we say at x equal to 0? Because the curve crosses what? The y-axis. And at that y-axis, x is 0. So now the gradient becomes 3. X is 0 minus 4. X is 0 plus 5. 0 squared is 0. Times 3 is 0. 0 times 4 is 0. Then 0 minus 0 is 0. 0 squared is 0. Times 3 is 0. 0 times 4 is 0. So what we have is 5. This is the gradient of this function when the curve crosses what? The y-axis. A similar one is here. We want to find the gradient of this curve again. But this time, at the point where the curve crosses the x-axis, not at the y, but at the x-axis. Okay. So let's find the gradient first and see. We say y is equal to, what do we do? How do we write this one? We say x over x minus 4 over x. Whenever you want to differentiate and the denominator contains x, of which it's just a single term and not an expression, you can manipulate to what? To avoid the denominator with variables. So we say any value divided by the same value is 1. So this x goes up and the sign of this power changes. So now we differentiate dy over dx. This term does not contain x. That makes it a constant term. Differentiating a constant term gives us 0 all the time. So we forget about this. We come to this. The power of the variable is minus 1. The coefficient is minus 1. So minus 1 times minus 1 is simply 4. Finally, the power we have minus 1. So it's like minus 1 minus 1, which is minus 2. So 4x to the minus 2. So this can also be written as 4 over x squared. We bring down the x, then the sign of the power changes. This is our first derivative. This is our gradient function. But what? We want to find the gradient at the point where the curve crosses the x-axis. So we say at x-axis, what happens? Y is 0. Likewise here, at y-axis, x is 0. At x-axis, y is 0. But the gradient function does not contain y. It contains x. Unlike here, the gradient function 3x squared minus 4x plus 5, it contains x. So we simply substituted the value for x. So here, the gradient function contains x, and this is y equal to 0. So we need x value that we can use to substitute. So what do we do? we go to the function that is given. So we say y equal to x minus 4 over x. But y is 0, so y is 0. So x minus 4 over x. Remember what we call, how do I call this? Fractions equal to 0. Whenever a fraction is equal to 0, the numerator is equal to 0. Defined and undefined fractions. Whenever a fraction is equal to 0, we say the numerator, x minus 4, is equal to 0. So when we move minus 4 to the right hand side, it becomes plus 4. So we can simply use this 4 and substitute to the gradient function. So now our gradient dy dx, which is 4 over x squared, is 4 over what is x now? Is 4. So 4 over 16. So this will give us 1 over 4. So suppose you need the answer in decimal, it will give us 0.25. So these are some of the examples we have today for gradient of a function. Thank you for watching. Don't forget to like and share. Bye bye.